In this video, we're going to learn how to draw ray diagrams for concave and convex mirrors, in other words, the curved mirrors in the course. Again, here are your learning goals. Make sure you go through them as you go through the presentation. We will also have the opportunity to do some lab exercises in order to learn the principles of light reflection off of curved mirrors, and you will use ray boxes just like you did with the plane mirror labs. Just as a review, you know that there are three types of mirrors. Plane mirrors, which are the flat ones. We've seen how to draw ray diagrams for those. We've also seen some applications of these plane mirrors. There are also curved mirrors, which fall under two main categories, concave mirrors and convex mirrors. Concave mirrors can be called converging mirrors, and we'll see why later on. It's what they do to light. They converge light rays. A concave mirror curves inwards. It looks like you're looking into a cave. A convex mirror curves outwards, and it's often called a diverging mirror because it makes light rays move away from each other, which means to diverge. So converge means to come close to each other, and that's what a concave mirror does. It makes light rays come close to each other, whereas a convex mirror makes light rays move away from each other, and that's called to diverge, and it curves outwards. So before we go into ray diagrams for curved mirrors, we need to look at what a curved mirror is, how it forms, and we need to learn some important terminology. So a curved mirror is often called a spherical mirror, and that's because it's made from a sphere. So if you had a sphere and you cut a piece of the sphere out, you would end up with a mirror. The if you had the inside of the sphere that was silvered, that would make a concave mirror, and if you had the outside of the sphere that was silver, that would make a convex mirror. So here we can see a sphere. If you cut a piece of that sphere out, you'll notice that the outside would be the convex part, and the inside that curves inwards would be the concave part. So over here we have our concave mirror curving inwards, and here we have our convex mirror curving outwards, and then there are some terms that we need to become familiar with before we can continue. So we have the principal axis and the center of curvature, which we'll see on the next slide. So here is our concave mirror that came out of the sphere. The first term you need to become familiar with is one called the vertex. It's represented by the letter A. It's essentially just the middle point of your mirror, whether it's concave or convex. So here we have our vertex represented by the letter A, the middle point of the mirror, and it cuts the mirror exactly in half. You have a line over here called the principal axis. The principal axis is the line that goes through the vertex. So the principal axis goes through the vertex. Another important point in this diagram is something called the focal point. So over here is our focal point. Different mirrors have different focal points. That's the point where light rays will actually converge to when they shine towards the mirror. The distance from the vertex to the focal point, that's called the focal length, and it's represented by lowercase f. So the focal point itself is the position where the light rays will focus to when they bounce off the mirror, but the focal length is the actual distance that you measure from the vertex to the focal point. Focal point represented by uppercase F, focal length by lowercase f. And then we get to another point called the center of curvature. That represents the radius, or the midpoint of the sphere from which the mirror was cut from. So this center of curvature is also actually considered the normal that light rays will reflect about. Kind of like you had a normal in your plane mirror that was 90 degrees to the mirror. The center of curvature happens to be located at the normal happens to be located at the center of curvature. The length from the vertex to the center of curvature is called the radius of curvature. And the interesting thing about the radius of curvature is that it's 2 times the focal length. So for example, let's say your focal length was 2 centimeters. It varies based on the mirror, but let's say the focal length was 2 centimeters. Well, then the radius of curvature would be 2 times that. So it would be 4 centimeters. Now, since the center of curvature is the center of the sphere from which the mirror was cut, we can say that the radius of curvature is also the radius of that sphere. The other terms that we learned for plane mirrors will still apply. So DI is going to be the distance of the image from the vertex. DO is going to be the distance of the object from the vertex. HI is still the height of the image. HO is still the height of the object. So you need to become very familiar with these terms. Center of curvature, know that it's represented by C. The vertex, know that it's represented by uppercase A. Focal point by uppercase F. Focal length by lowercase f. And the radius of curvature is the length from the vertex to the center of curvature, and it's basically just 2 times your focal length. The line that goes through the center of curvature, through the focal point, and then to the vertex is called the principal axis, sometimes abbreviated as PA. So this is a line that cuts the mirror exactly in half, and it passes through the center of curvature, through the focal point, and then to the vertex. So these mirrors do have several applications. One of the most common areas you may have seen, or one area you may have seen these mirrors before and actually been aware of them, is in a fun house. You might have seen it on TV if you haven't been in a real fun house, but they use several curved mirrors in order to get some distorted images. So when we're studying plane mirrors, the SALT description was pretty straightforward. The HI was always equal to HO, the attitude was always upright, the location was DI is always equal to DO, and the type was always virtual. When it comes to curved mirrors, like a concave mirror, the image type and other characteristics will vary based on where the object is. So if the object is closer to the mirror, farther away from the mirror, that will give you different image characteristics overall, which makes it a little bit more challenging, but with a bit of practice, you'll get the hang of it. Before we go into drawing ray diagrams for curved mirrors, we need to just focus a little bit more on the focal point. So here we have our concave mirror again, and notice we have the lines at the back to illustrate the back of the mirror, and then our concave mirror focuses inwards. So the reason that this is called the focal point over here is because when light rays that are parallel to each other and also parallel to the principal axis are aimed towards the mirror, they will reflect, so bounce off the mirror, and meet at the focal point. So that point where all those light rays that were parallel to each other and to the principal axis meet, once they reflect, that is called the focal point. And so this is the reason why these concave mirrors are called converging mirrors, because as you can see here, all of these light rays, they converge onto a single point. So this mirror causes the light rays to converge, to come close together. So if you want to determine where the focal point is, experimentally, you'd have to aim a bunch of light rays parallel to each other and to the principal axis towards a mirror, and then see where all the light rays meet up, and that would be your focal point. Once you find your focal point, then you can measure with a ruler the focal length. So let's say it's, again, 2 centimeters, then you can find the center of curvature by multiplying that by 2, and that would be your center of curvature. Just 2 times the focal length with an uppercase C. So as I mentioned, with a plane mirror, SALT was always the same, regardless of the distance. However, with concave mirrors, which is what we're going to start off with, the image characteristics will vary based on where the object is located, and we're going to take a look at the different cases that we have. So here are the steps for drawing the ray diagrams for curved mirrors, specifically for concave mirrors. We're going to start off with that and then go into convex mirrors at the end. So your first step is to draw the principal axis, so the line that cuts the mirror exactly in half, and to also mark your points, the focal point, and then the 2 times the focal point. So in other words, your center of curvature as well. The reason for that is that oftentimes when we do labs, we will speak in terms of focal lengths for distances of objects. So for example, if I told you the object is located 1 focal length away from the mirror, that means it's at the focal point. If I said it was 2 focal lengths away from the mirror, that means it's at the center of curvature. Let's say the focal length was 2 centimeters. Well, 2 focal lengths would be 4 centimeters away from the mirror or away from the vertex. If I said that the object was located 3 focal lengths away from the mirror, that would be 3 times 2, which is 1 focal length, would be 6 centimeters away from the mirror. So oftentimes we will represent distances in concave and convex mirrors using focal length terms, which is why you need to become familiar with that. And again, the reason I have an uppercase F here is because this is the focal point, and over here an uppercase C because we have the center of curvature. But if I measured the distance from the vertex, this should actually be represented by A, not V. If I measure the distance from the vertex to the center of curvature, that would be the radius of curvature, and then the distance from the vertex to the focal point, that would be the focal length. So the first step is placing your object on the principal axis. You want to put the base of the object on the principal axis, and then you'll have an arrow again so that you can keep track of the orientation. Now, the law of reflection does apply to curved mirrors, but the normal is not quite perpendicular to the actual surface of the mirror, but is perpendicular to something behind the mirror that's imaginary called a tangent. You'll learn more about that in grade 11, but basically it's just a line that touches a single point on this mirror. And so you won't really need to draw that line because you need an equation in order to do that. So what we're going to do is we're going to memorize a few special rays that you can use, and you can predict where they reflect without having to measure really any of the angles. So in this case here, just to go back to the distance rule that we discussed, this object is more than 2 focal lengths away. So for example, this would be 1 focal length, this would be 2 focal lengths, and it looks like it's about 2.5 focal lengths away. So here you can see our example. If the focal length was 3 centimeters and an object is 2 focal lengths away, then it would be 6 centimeters away. If it was 3 focal lengths away, then it would be 9 centimeters away. So our first ray that we should draw, our first special ray, is a ray that goes from the top of the object that's parallel to the principal axis, and it goes towards the mirror and hits the mirror. Notice again that this is an incident ray, so the arrow has to point into the mirror. Any ray that's parallel to the principal axis and hits a concave mirror will reflect through the focal point. If you were to draw the tangent behind the mirror, you would actually see. So I'm going to draw the tangent. This mirror is not really well drawn here, but I'll make my normal along the tangent. And if you continued doing that normal, it would cut through the center of curvature. So the normal actually always goes through the center of curvature. And it still does obey the law of reflection. If this was 15 degrees, so would this be. Theta I is equal to theta R. But we don't have to represent that. I'm just showing you that it does follow the law of reflection even though it's not a plane mirror. So our first ray was one parallel to the principal axis. and that reflected towards the focal point, and you keep on drawing it going through the focal point. Extend it because we don't know where our image will end up, so you want to extend it far enough to actually get rays that cross. The second special ray that we're going to use is one that goes to the vertex. Now for this one here, you'll actually have to measure the angle of incidence. And since we have our principal axis as our normal, we can easily measure that angle of incidence. So let's say this is theta I, then it'll reflect according to the law of reflection. So you measure theta R and then draw your reflected ray accordingly. So this would be equal to theta R. Now at this point, we actually have two reflected rays that intersect. Your image will form where the two reflected rays intersect. Don't draw your image here. I know there's rays intersecting, but it's not two reflected rays. That's an incident and a reflected. It has to be two reflected rays, so two of the green ones here. But there's another special ray that you can use, and I'm going to show you that special ray before we actually draw in our image. So before we actually draw our image, we're going to look at the last special ray, and that's a ray that goes through the focal point. A ray that goes through the focal point will reflect parallel to the principal axis. Now, I am a little bit off with my measurements here, but where they all intersect, which is roughly about here, is where the top of your object will be, because the light rays came from the top of the object. So rather, I should say the top of the image will be. And so I'll make my arrow pointing down. And I'm just going to put my arrow tail back on the base. So the tail stays on the base, but the head is now facing down. So as you guessed it, this image is no longer upright compared to the object. It's actually inverted compared to the object. Another thing you'll notice is that the image is actually formed by real rays in front of the mirror. So it's real rays here. These aren't traceback rays anymore. Because those are real rays, this image is a real image. You'll also notice that the height is smaller than the height of the image is smaller than the height of the object. And you'll also notice that the image is actually closer to the mirror than the object was. So we can describe image characteristics we can describe the image characteristics using SALT. So again, if you're looking at the type of image, we know it's a real image. So that's our T in SALT. We can describe the location, the L in SALT. Our DO is larger than DI, and you could actually measure that DO with the ruler to see how far it is, and the DI with the ruler to see how far it is if you're ever unsure. We could measure the size as well. We can see our HO is greater than our HI, and again, you can measure if you're not sure. And then our orientation or our attitude, the A in SALT. As you can see, the image is inverted this time. It is not upright like we saw in plane mirrors. So when the object is more than 2 focal lengths away for a concave mirror, the image will be inverted, smaller, closer to the mirror, and real. It doesn't matter where beyond the center of curvature you are. It doesn't matter if you're, let's say, over here, or over here, or over here, or over here, or over here. The image will always be smaller, real, closer to the mirror, and inverted for the case where you are more than 2 focal lengths away. So your goal is to practice doing ray diagrams for a variety of different objects at a variety of locations. So you might have an object located at the focal point. You might have an object located between the focal point and the vertex. You might have, so that's right before the focal point. You might have an object located between 1 and 2 focal points, or rather focal lengths, so in between F and C. You might have an object at the center of curvature. and you need to use salt in order to describe the image characteristics that are formed. When there is an optional step that you might have to take that I did not show you in the previous example, sometimes it'll appear like the reflected rays are not approaching each other, not converging. In that case, what you'll have to do is you'll have to draw tracebacks behind the mirror, because perhaps you might have a virtual image forming. So you should be able to do a ray diagram for something beyond 2 focal lengths. You should be able to do a ray diagram for something at 2 focal lengths. You should be able to do a ray diagram for something between 2 focal lengths and 1 focal length. So in other words, between the focal point and the center of curvature. You should also be able to do a ray diagram for something at the focal point, so 1 focal length away, and a ray diagram for something between the focal point and the vertex. I'll give you a hint. For this scenario and the scenario where you are at the focal length, you may have to do tracebacks. So here we have a little animation showing the formation of an image for an object that was placed at the center of curvature. You can see the incident ray that's parallel to the principal axis reflect towards the focal point over here, and you can see the incident ray that goes through the focal point reflects parallel to the principal axis, and they meet at this point over here. Since those light rays came from the candle flame is now here, and the base stays below. As you can see from the scenario here, when an object is placed at the center of curvature, it does form an inverted image. It is a real image as well because it's formed by these real rays. And you'll also notice that the distance of the object to the vertex is the same as the distance of the image to the vertex. So di is equal to do. And the height of the object is actually the same as the height as the image. So hi is equal to ho. So here we have a spoon, and you are looking into the concave part of a spoon. Now, if your image is inverted and smaller than you are, where would you be relative to that spoon's focal point? Once you do enough ray diagrams, you'll be able to answer this question. In the next few slides, I have answers to the various cases that I told you to attempt. So for example, when you're at the center of curvature, so 2 focal lengths away or 2 focal points, you can say as well. When you're between the center of curvature and the focal point, your image, you'll notice, is going to be larger, it's going to be farther away, so di is larger than do, it's going to be real, and it's going to be inverted. When you're at the focal point, you would have drawn your tracebacks, your reflected rays. You'll notice that those tracebacks and reflected rays are parallel to each other, so they'll actually never meet. And so at the focal point, there's actually no image that forms. So if you obtained that answer when you were doing your ray diagrams, then you were right. I know it seemed bizarre, but there's actually there's no image that forms when the object is placed at the focal point of that mirror, because the light rays that are reflected will actually never meet, and neither will the ones that are drawn as tracebacks. And then over here we can see the scenario where you have the object in between one focal point and the vertex. And as you can see, the image is a virtual image. It's formed by traceback rays that actually do meet up. You'll notice that the di is larger than do, the hi is larger than ho, and the image is upright. And as I said before, virtual, formed by tracebacks. So with a concave mirror, as you can see, the type of image, the attitude of the image, the location and size of the image all vary depending on where the object is placed in terms of focal lengths. So you need to become familiar with the different cases, so when you have a multiple choice question or a question you have to answer rapidly, you can easily come up with an answer, or you know how to verify your answer when you do a ray diagram. In this image over here, I want you to identify the trend as the distance of the object increases. The objects in this case are represented in red, and the images are represented in blue. So for example, if you look at object 9, it is very close to the mirror, its image is very close to the mirror. If you look at object 8, it is a bit farther away from the mirror. Its image is a little bit farther away from the mirror. Object 7, it's farther away than 8 is from the mirror, and image 7 is farther away than image 8 or 9 are from the mirror. So think of the trend that you notice there. Also think of the trend in terms of size. Look at the size of images 9, 8, and 7 as these move away from the mirror. So I recommend that when you observe the trends, you do it in segments. First, look at the trends as you're moving away from the mirror towards the focal point. At the focal point, object 6 doesn't seem to have a corresponding image. Think about why that is. Now when you're between F and C, take a look at what's happening. Here you have object 5. Here you have image 5. Here you have object 4. Here you have image 4. So between F and C, as you move away from the mirror, what tends to happen to the image distance? Take a look at C. As you can see, object 3 has its image directly below it. And then you can look at the segments beyond the center of curvature. So here you have object 2, image 2, object 1, image 1. As you go farther and farther away from the mirror beyond the center of curvature, it seems like the image is coming closer and closer to the mirror. So try to approach the trends in terms of those chunks between vertex and F, between F and C, and then beyond C. And write as many trends as you can notice with this image here. This here is a summary of the different image characteristics that you'll see for concave mirrors based on the object location. I do want you to fill that out once you're done all your ray diagrams so you know what to expect when you do a ray diagram on a quiz or a test. So we just finished looking at concave mirrors, which are converging mirrors. Now we're going to take a quick look at convex mirrors. They're actually a little bit easier because they only really have one case that gives you the same image characteristics all the time in a similar fashion to plane mirrors. So the terms that we learned, principal axis, center of curvature, focal length, focal point, center, radius of curvature, all still apply, but this time we're going to be facing the side of the mirror that curves outwards. So the outward part is silvered instead. So we're going to use ray diagrams to predict where an image will form. Again, same terms apply. This is the part of the mirror you'd be looking into. All the important terms are sort of imaginary. They're behind the mirror this time. So the focal point will be behind the mirror. It'll actually be a virtual focal point. If you have a distance from the vertex to the focal point, that's the focal length, and then the radius of curvature is still the distance from the vertex to the center of curvature, just like we saw in the case for concave mirrors, except everything is, again, behind the mirror, so almost as if they're all virtual. DI still means the same thing, DO still means the same thing with HI and HO. So over here we're going to see why the convex mirror is called a diverging mirror. When there are light rays that are parallel to each other and parallel to the principal axis, you'll notice that when they reflect away from each other. So these light rays are moving away from each other, which is what we refer to as diverging. Diverging means to move away from each other. So they do diverge away from each other, and you'll notice that they'll never meet because they do move away from each other. However, if you extend the tracebacks of those reflected rays from the incident rays that were parallel to each other and to the principal axis, the tracebacks will actually appear to meet behind the mirror, and that's where the focal point will be. So you have really a virtual or imaginary focal point where the tracebacks meet in the case of a convex mirror. So we often say that the focal length for a convex mirror is negative because it's behind the mirror. That will come in handy later on when we see something called the mirror or thin lens equation. Here we have our steps to drawing the ray diagrams for a convex mirror. And again, these steps are a lot easier because you'll always have one image characteristic for convex mirrors. The distance doesn't really matter too much. So our first step is to draw our principal axis. Make sure that your focal point's on there. Place the base of the object on the principal axis, and the arrow points upwards for your object initially. So again, the focal point is behind the mirror at this point. The first ray is going to go from the top of the object towards the mirror, and it will reflect as if it's coming out from the focal point behind the mirror. Make your trace back. You are going to make your trace back ray now extend behind the mirror. So what I would do is even before lifting your ruler, I would extend that trace back ray behind the mirror. I'm going to show this later on in the animation, but you would extend that trace back ray behind the mirror, and it goes towards the focal point. The other ray that you're going to see is one that goes to the vertex. You measure the theta I, and then you use that to find your theta R. And so that's where you would draw your reflected ray according to the law of reflection. And again, same idea. I'm going to show it later on in the animation, but before lifting your ruler, draw the trace back ray of that reflected ray. The last ray that you can draw is one that goes towards the focal point on the other side. So you want to aim your ruler, line it up from the top of the object towards the focal point on the other side, but there's a mirror in the way, so your incident ray cannot go through the mirror, so it hits the mirror and reflects. It reflects parallel to the principal axis. And again, you would make the trace back for that ray as well. So your final step is really, if you haven't done so already, make your trace backs for all the reflected rays. One for the first special ray, one for the second special ray, and one for the third special ray. The point where they all meet up will be the arrowhead, or the image head, and the base will stay on the principal axis, so that is where your image will be. So as you can see, the image is a virtual one this time because it's made by trace back rays. The image is going to be smaller, so HI is smaller than HO. It's going to be closer to the mirror, so DI is smaller than DO, and it's going to be upright. And so that's the case for all the images formed, regardless of the position or the distance of the object from the mirror. So you're not going to have all those different cases at one focal point, at two focal points. It's just always going to be a smaller, upright, virtual, closer image to the mirror. For the case of convex mirrors. So they're a bit more similar to the plane mirrors than the concave mirrors were in terms of the types of images that can form. In order to see an image formed by one of these curved mirrors, your eye just has to be in the way of one of the reflected rays coming off the mirror, or a few of the reflected rays coming off the mirror. So if your eye is over here, you can see part of the image. If it's over here, you can see part of the image. If it's over here, you can see part of the image. So if your eye is in the way of these reflected rays, then you will be able to see the image. And again, if in some cases you might have an image that forms in front of the mirror, so it'll look kind of like a hologram. And in some cases, you'll have it form behind the mirror. In convex cases, it's always going to be behind the mirror. So now I'd like you to find the trend that you notice for the convex mirror case. Again, the objects are in red and the images are in blue. See what happens as you approach the mirror to your image distance, your image height, and any other trends that you may notice. List them on this image here, because it'll help you to answer multiple choice questions more effectively without having to draw a ray diagram every single time, or to double check your answers when you are doing a ray diagram. And here we have a table that you should fill out to just make a summary for the convex mirror image properties. And as you know, you won't have to fill out this entire table, because you know that you're always going to get the same type of image properties regardless of the distance from the mirror. So here we have our summary for the concave and convex mirrors. You should know how to do ray diagrams for the concave mirrors, and for the convex mirrors you should know all of the different cases for the concave mirrors and the only case for the convex mirrors. This is a summary from your textbook of the different cases for the concave mirror. The only one that's not really shown is the case where you are more than 2 focal lengths away. But you should know how to do that with enough, is the case where you are 2 focal lengths away. And you should know how to do that one despite it not being here with enough practice from your worksheets. Over here we have the scenario for the convex mirror, and there's only really one scenario, so you should be able to demonstrate that using a ray diagram. Now we're going to take a quick look at the curved mirrors in terms of their application. So we'll look at the concave mirror applications and the convex mirror applications. I'm going to go through them quickly, but I do expect you to read up on these applications in a bit more detail in your textbook. So over here we can see the applications of concave mirrors. Concave mirrors are used in flashlights. So there's basically a light bulb placed in the center of the concave mirror. When you turn the light bulb on, light rays will leave from the focal point, hit the mirror, and travel parallel to each other to make a beam of light that can illuminate the surface that you shine it onto. Telescopes will use a concave mirror in order to focus light onto a certain point. So for example, here you would have your eye. Here you would have light from the object that you're observing enter the telescope. This here is a concave mirror. Since these light rays are parallel to each other, they go towards the focal point where another mirror has been placed. Those light rays will bounce off of that mirror and then go into your eye, and you can observe the object that you're trying to watch in space. Cosmetic mirrors will make you look larger, and based on that information, knowing that it's concave, you should be able to figure out where you are relative to that mirror's focal point. Same thing with the headlights of a car. They work in a similar way to a flashlight, with the light bulb placed at the focal point to make rays that are parallel to each other when they come out to make a nice beam of light for you to see. So over here we can just see a ray diagram of a light bulb within a flashlight. That light bulb, like I said, is placed at the focal point so that when light rays hit the mirror, the concave mirror within the flashlight, they're all parallel to each other to make a beam of light. And again, remember, a light beam is many light rays going in the same direction. Here we just zoomed in to take a look at the telescope with this concave mirror over here to focus light onto another mirror over here, which will reflect all that light into your eye over here, so you can actually see the image of the object that you're watching from over here, from far away in the distance. Because it's so far away, its light rays are parallel to each other. You'll understand why later on, but the farther away an object is from you, the more parallel its light rays are going to be to each other when they actually approach the mirror or the object you're trying to observe it with. Another application of concave mirrors is that of spotlights and satellites. So for a spotlight, it's the same idea as a flashlight. You have a light bulb placed at the focal point. You turn on the light bulb, light rays go through the focal point and are reflected parallel to each other to make a nice beam of light. Satellites, when they collect signals from the electromagnetic spectrum, the signals will hit the concave dish and then hit a sensor placed at the focal point, because light rays that are parallel to each other and parallel to the principal axis will reflect towards that focal point, which is where you would place your sensor. Here is our cosmetic mirror or makeup mirror. Again, you should now be able to tell me where you are relative to the object's, relative to the mirror's focal point, because you are an upright, virtual, larger image. Another application of concave mirrors are these solar ovens. So the idea is that it's a concave dish. You place the food or item you're trying to heat up at the focal point. Light rays from the sun that are parallel to each other and to the principal axis will be focused towards the focal point when they are reflected, and that will allow them to heat up your food that you placed at that focal point. And here there's a little bit of a problem that you should be able to solve with your knowledge of terminology such as center of curvature, focal length, focal point, and radius of curvature. Dental mirrors are also concave. They allow the dentist to see a magnified view within your mouth, so the dentist can work more effectively on the cavity or whatever the process is that they're working on at that time. Convex mirrors also have several applications. You might have seen them in many stores when you go shopping. You'll notice that they shrink everything, so you always get a smaller image, but that's a good thing because you can fit the entire store within that convex mirror, so you can get a better view of everyone who's doing the shopping. We'll often use these convex mirrors at border crossings to basically fit the entire underside of your car within the mirror, so we can see if we're trying to smuggle anything across the border. The side view mirrors, you'll often see this writing in it that says objects in mirror are closer than they appear, and that's well because they are convex mirrors. If you ever go to an ATM, you might sometimes see the convex mirror placed on the ATM so you can get a wide view of what's behind you for security reasons as well. So these convex mirrors, they do make smaller images. They try to fit everything into them so you can get a better view of your surroundings with them. So the characteristics of the images produced by a mirror will determine what they're used for in society. And that seems to be a common theme that we've seen in science courses. Here we just have a summary of the different image characteristics for the concave and convex mirrors based on the location. So based on that concept, you should be able, based on your drawings, you should be able to fill in a table just like this to summarize your understanding. And over here we just have a summary of all the image characteristics for all the different mirrors that we've seen for convex and concave and plane mirrors as well. To practice, you should read page 496 to 501, do questions on page 501. They're all applicable and you should be able to solve them at this point. There will be some worksheets provided to you, so please do attempt those, and also the homework slide problems for the different cases of concave and convex mirrors. I do want you to read up on a few more applications of curved mirrors. You'll see them in your textbook, and you'll also see some videos online as you do some research.